All right, so this is section 3 on text data and lecture 17, naive-Bayes classifier for text classification. And so in this section, I will talk about the naive-Bayes classifier and generative Bayes classifier and how to apply them on text data. So I will reuse some of my last fall's recording, and then let's get started.
Right, so again, it's our nutshell, and we are using the joint probability instead of conditional probability. It's joint probability of x condition C times PC to perform the classification. And we have covered the Bernoulli type of model to. So the differences is really in how do you use model, this generated model, when you condition on each class labels. So we already covered the Bernoulli model. We also covered Gaussian model. Actually, in the Gaussian case, we have naive version and also the non-naive version. And today we're going to cover, it's called the multinomial naive-Bayes classifier. Okay, just to recap, when we talk about a generative Bayes classifier, what we truly estimate is for each class label, we have a generative model. And we need to estimate the parameter for each possible class labels. And at the same time, we need to estimate the priors of each class too. And we're using this decision functions to perform. This is the MAP decision function to use this rule to figure out who is the most likely class. And the naive-Bayes classifier, in fact, just having the assumption of this joint conditional probability of x1 to xp is equivalent to each of the marginal conditional probability just times together. All right, so this is today's content. So I'm going to first talk about how do you represent a text document. And then there's will be two models, two naive-Bayes classifier models which are normally popular to represent text data, to perform text-based prediction models before. And the first one is called multivariate Bernoulli model, and the second is called multinomial Bayes classification model. And so for each of those, I will talk about how do you test, how do you train, and then this is exactly how you're going to figure out or implement in the homework 5. All right, so this has a lot of overlaps if you're taking information retrieval or you already took text categorization course. But I still want to cover this because it's fairly basic, but a lot of students, if they never took text retrieval course, they don't understand this. Maybe let me just roughly give a guess. So who hasn't learned about bag of words representation? Can you raise your hand? Oh, well, who hasn't learned? Okay, pretty small number. Okay, so in the end, just the basic task is to classify a text article into some classes. So for example, in the classic case, it's spam email classification. So the input is this email, the full email text, and output is this a spam or not a spam? So in fact, like if we're using probability type of model, we're predicting PC condition on the document. So here, I used to use X, but just let me use D this time, just representing this is text document. So let's just again talk about history. So why naive-Bayes? Similar to any of the other classification model which kind of dominating at a certain stage before. All right. Yeah, so let's go on. So in this literature of data-driven models, and it's always because of competition winning results makes the some classifier cannot dominate. In the case of naive-Bayes, it won the competition in KDD Cup, which is pretty old, of course, 1997, in a text, a mail-based. Alif, can you help me check? So this is really just trying to predict if a recipient of email will actually respond to an advertisement. So there are about like 750K records in that competition. So this is a very, very big amount of data in 1997. If you still remember this year, this is a very magic year for the deep learning. The convolution neural nets was kind of designed or first out by Yang Wukong in 1998, and the recurrent neural nets was out in 1997. But both approach could not just even, they are just too difficult to implement, and at that time it's actually is decision tree and naive-Bayes, and then later it's SVM dominating the whole industry, so performing data-driven predictions. So naive-Bayes is a very good solid baseline for text classification, but not the best. And for most text categorization, the main issue here is there's certain property is for text-based classification. There are many relevant features, but also there are many irrelevant features. So which type of method, if you think about it, can handle or nicely handle when you have so many features? Some of those are relevant, some are irrelevant. And also the relevance among the useful features are quite similar to each other. All right, so just to give you a few examples of other type of text classification applications. Yeah, so we can perform spam email classification, web page classification, which was actually a very classic task by then. And we're going to have an example to show you. So, and then there's news categorization, which is pretty dominant if you think of Google News. It's a very, it's exactly doing this automatic news story classification. And the movie reviews, which is the sentiment recommendation, which exactly is this type of classification. So actually, in fact, in the literature, so how do you even know what task is important? Researchers just design and think and then propose. For example, sentiment classification was never even used before by those IMDb, but just one researcher from Cornell, they just think, why not? Can you do a text-based polarity prediction? And then immediately Netflix and Amazon Reviews or TripAdvisor realized, wow, such a great tool can ease the whole pipelines of their running. So they adopted the sentiment classification, which becomes a dominating application now. So yeah, like email classification is also a dominating function, and almost every email provider is using that. Okay, so this is just to show you an example of Google News classification. This is actually what I just captured like 2 hours ago. I mean, Google News just automatically categorize the news into categories, right? So this category, in fact, it's more like a tree, a shape of a tree. And I'm just using science today, so NASA, and then this actually it's pretty easy if you feel like there are certain special words. It's most likely to appear in the science category, right? There are certain kind of words most likely to appear in the politic type of kind. So that's the basic intuition behind text classification. Okay, so first question is, how do you even represent it? So your text articles are input as just a string of words. And the string of words, I mean, you don't know its length, right? Because different news articles, there are some shorter, some are longer. How do you represent it? So the issue just how do you represent it? So in the end, the most classic representation is called bag of words representation. So that's the problem. You want to classify this article or this piece of reviews into a class. And then this is how you truly represent to a classifier. So in here, you're saying, I love the movie, it's sweet, and then whatever, it's great. And then here, you actually just forget about the concrete phrases or whatever. You just leave a vector with a fixed size, which is the dictionary size. And for each entries, it corresponded to a specific word in that dictionary. And the numbers they are representing how many times the occurrence of that specific word in the article. This is called a bag of word representation. And then you're just performing the predictive models on this vector formulation. So, but how do you convert this into this? There are a few steps. So when we are giving you this data, so the data is just a lot of different articles, right? Some are classified as positive, some are classified as negative. And how do you convert each article into a vector? And the first question is, who is even that dictionary representing? And how do you get the dictionary? So in fact, this is a very difficult step. So in the homework, we give you a simplified version, which is predefined 16 words. Honestly, this is a very bad, weird choice. The reason is just for those students who doesn't want to mess around with NLTK, you can just go with the 16-word choice. For those who actually want to play with NLTK, please do so. Okay, so in NLTK, you need to figure out, it's actually pretty easy. The library is very mature. It needs to perform first to remove the stop words. Stop words is mostly likely is those words really doesn't have any meaning at all. So for example, maybe or a. To have this word, I mean, it really doesn't tell you anything, right? So in a lot of cases, this is removed in the dictionary, from the dictionary. There are a lot of other words like is. I think some cases is kept. It depends on this rule of what it's strict or it's less strict. There are different variations of stopping words removal. And then, so this is the first step. After you remove the stop words, and then you have to convert, for a word, you normally have different appearance, like love, loves, loving. You want to match it to the same word, love. So this step is called stemming. And in the NLTK is the tokenizer. There are actually multiple different tokenizers. Again, play with it. And so you can go with the choice that directly using NLTK to construct a good dictionary. Or you just use the weird small dictionary we proposed, and that's totally good too. Question about this? Because I already see a student posting question on Piazza about this. All right. Okay, so now you have a dictionary, and then you need to do counting. You need to count how is each word appeared in a specific document. That specific document is your sample, a sample, right? You need to do this frequency counting of each word in the dictionary. So assuming your word dictionary is W1, W2, until WK, and that's your dictionary, then you can represent the text into a vector of word frequencies. So, but this is actually just one possible choice, right? You can also make an even more simplified choice is you just check has that word appeared in the article or not. And the only thing you recorded in the vector is yes or no. This makes each value or each entry of vector into a binary representation. And even more, you can convert the count, or you can use some kind of normalized count. There are many choices. So the popular choice, this is actually there are many papers in information retrieval just trying to figure out what is the right number or right way of numbers to put as per word appeared in the article. So very classic is something called EM25, and it's actually TF-IDF date. I don't want to cover more, just feel free to check it out. But I think in the homework, let's just use the count. Used count is good enough. But I want to let you know the state-of-the-art information retrieval systems not directly using count. It's something relevant to count, plus some kind of normalization. All right, so now you get, for your data, you're getting the matrix now. So now that many files, which is the one we actually shared you, each file converted is the per file, right? It's per file, it's per sample. Yeah, I remember. So each file there becomes a row in a matrix form. And each row representing a specific document. And in here we have 0 until 900 document, just to show you a rough, speculated number. And each column here showing you the dictionary words. About the dictionary words, W1, W2, until W, I think we use the capital B or capital D to represent the size. Maybe B, yeah. All the possible words, so each entry xij is just the frequency of word j in the document I. So now this is a matrix form. Then you can just apply, anything can be applied on the matrix form to perform prediction. So So the issue is, first of all, the vocabulary size, it's actually very tricky. So if you have too big vocabulary, so assuming let's just don't even use NLTK, forget about all those stemming, forget about stop words too, you really just use a hash function. The simplest, just performing hashing. Do the hash array, put whatever unique string labels from your current data into a hash. And that's actually your dictionary, right? Because those are the unique string. The unique strings happen in my data. However, this is a bad choice, so they're most likely, just like the one I just showed, love, loving, loves, the three things match to three different unique hash keys. But in fact, they represent similar semantics, right? They should be matched to the same hash key. So that's the first reason why it's bad. The other reason is this type of hashing or uniqueness-based dictionary building, you have a a lot of those unique strings appeared only once, appear only or even only twice. It's really difficult if you observe it only once or twice to estimate, to perform a solid or credible justification about its frequency, about its probability, conditioned on a certain document, and then hopefully to generalize better. So that's why the real word, it's a bad thing you want to avoid when you handle the text data. So, which easily you can do using the hash. You use the value of each hashing as the frequency, right? That's the easiest way to build this dictionary. And then you're just cut. So the pretty classic approach is after stemming, after removing the stop words, and then performing the hashing, and then sorted by the frequencies, you normally try to remove, you should remove. Those words appeared smaller than maybe 5 times in your training data. So it's just a magic 5, give you a good practice. Okay, so this gives you the training data dictionary, right? But that's just my training database dictionary building. When there's a future text article coming, it's highly likely, and there are words just can't be matched to any of the dictionary words you have. How would you handle it? So this is just classic problem, or very, very classic problem called out of vocabulary problem. And then people just use this a strategy called unknown. So I'm adding an unknown token in my dictionary. Whatever is rare, whatever is unknown, I will assign unknown as its token.
Great. So this is the end of this module. See you in next module.